Okay, welcome everyone to this continuation of what is quantum topology. So, quantum topology, and we're already thinking about monoidal categories. And today I would like to tell you about one very, very crucial thing about monoidal categories. There is a process called strictification, which everyone likes, in the following sense. So, monoidal categories have this very strange definition. Yeah, so I can actually pull it up again. Just 1 second. So in the previous definition, we had this funny definition with all these natural isomorphisms, those associators and the unitors here. And then all these associativity constraints, this one, and yeah, it's a lot of data and nobody really wants to do that. And it turns out that you can completely ignore it. So here, what you see here, what you saw last time is what is called, well, a monoidal category in general. And today I would like to tell you about the strict version of it, which are diagrams, right? So strict is, for me, is always diagrammatics. And next time I will actually make this a bit more precise, because there's one of my favorite examples of all of this is this vector G thing, and there's a diagrammatic description of it. And it's really beautiful. And this is kind of the standard example of something that you, but the strictification is not what you think it is. That's really, really, really nice. So, if you've never seen too much diagrammatics before, but maybe you're an expert on monoidal categories, this vector G example is really cute. It will tell you actually how the strictification works. But for today, you don't really need to know that. Let me just tell you the following. So if you just think about associativity, right, of a ring, of a group, of whatever, some object, multiplication in arithmetic, standard multiplication, 3 times 4 times 5. What people usually never tell you is that there are brackets involved. Right? You immediately forget that. Associativity, nobody cares about that bullshit. But strictly speaking, whenever you have such a definition, you should have this definition that your multiplication structure satisfies h times g times f equals h times g times f, and just the difference is just how you bracket things, right? So this literally this. And I usually like to draw it in this little tree type thing. So f, h, g, f. So if I put the bracket on gf, I first merge g and f, and then h merges. So every merge essentially corresponds to a bracket. So there would be an outer bracket as well, right? It decided to ignore the outer bracket. And if you do it the other way around, you have the inner bracket here, because this little leg here has moved from here to here. So that's a diagrammatic description of a diagrammatic picture of associativity. And that's what it is. But associativity, so that's what you usually learn, right? Associativity is this A-type thing, right? HGF equals HGF. But the correct thing to say would be any bracketing is the same, right? The result is independent of the bracketing, of the parentheses. But somehow, for some reasons, this is what people usually tell you is associativity. Just that thing. But what it really should say is I can move my legs arbitrarily around. Right? This you'll see a slightly better picture in a second. But essentially, philosophically correct is definition B, right? Every kind of way to put your brackets, your parentheses, gives the same result. But what people usually don't do, they just impose A, right? Tell you that's associativity, and then say, well, they don't say it, that's what I said. That's what I was trying to say. So what they should say is A is equivalent to B, and because it is, and that's non-trivial. And then you're happy, then, because B is actually what you want. Then you can forget about brackets, forget about parentheses, if you the B, right? Not in A. In A, it's not immediate. And that's why there's this tricky step, which usually people never tell you about, that A is actually equivalent to B. And yeah, it's a strategical interlude in this case. So here I have 4 symbols, so H, F, G, E, I guess, and the different ways of put parentheses onto them. So whatever. This one. So associativity should say that they're all the same, right? No parentheses. Any way of putting parentheses is the same. And it's not quite clear why this little operation here, where you just swap one leg over, implies that all of these 5 pictures are the same. but you can just do it stepwise. So here, so I can just swap that leg over to here, right? And it's here. And then I can just swap that leg over. I'm here. I can swap this leg over to here, and from here to here I can just swap that leg over, and then I'm around, right? So essentially the saying, I just have this graph here where I connect these different parentheses by an edge if they're related by one application of this simple, easy, small type of, well, associativity relation. And essentially, the A is equivalent to B is a statement that this graph is connected. And that's called a coherence theorem. The coherence theorem essentially says that some small relation of where to put parentheses, what is allowed, what kind of parentheses swaps are allowed, implies all possible parentheses swaps. That's coherence theorem. Coherence theorem. Very complicated name. Coherence theorem. Oh my god. It's equivalent to you can strictify everything. Yeah. So you don't need brackets at all. That's called strictification. And usually you have this proof, which you may not even have seen, even if you have studied mathematics for a long time. You might not have ever seen the proof that A is equivalent to B, because people usually never tell you. But A is equivalent to B, right? So this little type of operation, this little type of swap implies a general swap. And you can give a geometric proof by just saying this graph is connected. And why would we do that? Well, just keep that in mind. We'll come back to that in a second. So why would we need that, actually? Zoom out a little bit. Because essentially nothing you ever see is, well, strict. You can't forget brackets. It's a bit more tricky in categories than in standard arithmetic. Just think about the category of sets. Well, set. And you have three sets, x, y, z. And the two ways of bracketing them don't give the same result. Right? So here an element would be an x, comma, and then bracket y, comma, z. And here an element would be an x, comma, y, bracket, comma, z. Not quite the same thing. So set theory is super inflexible. So these guys are not the same in set theory. But of course, and they always look the same, right? So they should be the same. And the whole idea of category theory is that we can just identify them. Yeah, category is much more flexible, so we can just say they're equivalent. So set is equivalent to a category where they're all the same. Right? So if we would do that in set with the monoidal product being, well, the Cartesian product, then this is not the same. So right, so we would need parentheses. That's why last time, and that's why people usually start with this, give you this crazy definition of a monoidal category, because you need all of these parentheses, even in the easiest category you can imagine, the category of sets, right? Even in this category, you need those parentheses. It's kind of, yeah, well, what can you do? But category theory is flexible. So the whole idea is to get rid of parentheses by just sending set to an equivalent category where those guys are just spot on the same. That's the whole idea. And turns out you can do that. So a strict monoidal category is what we want to do is really just a category with a tensor product. There is no, there are no parentheses. There are just identity laws and whatever. It's really simple. Just exactly what you would think it should be. Now let's compare to the other thing. So this is what it should be, right? There is an extra operation on your category which applies to objects and morphisms, and that's just it. And it's a multiplication type structure. And here you have this extra operation, and then you have an associator, and a choice of an associator, a choice of a unitor, such that some crazy pentagon equation and triangle equation holds. So much more difficult. There's a choice involved for every triple of objects, and here's another one, and here's another one. Ah, my god. And this is much cleaner. We just literally have it. So this implies, associativity implies no brackets at all, right? I just told you that. It's kind of bad. I choose the bad definition because I should have said that thing, but I already told you that's equivalent to A anyway. So that's it. And the theorem, the big theorem, coherent theorem, strictification theorem, whatever you want to call it, is that every monoidal category, so the one where you have this whole strange back of, well, associators, unitors, oh my god, is equivalent to one of those guys, which is really nice, because this is the definition I would like to read, right? So you have an additional operation of multiplication. You can multiply objects and you can multiply morphisms. That's just it. It's just multiplication. And this is a really cool theorem. And the way to prove this is not completely trivial. You essentially say that every monoidal category is equivalent to a category of functors. And categories of functors are strict because, well, tensor product in this case would just be composition. Composition is strict. The only strict operation you ever know is composition anyway. So let me give you some examples, and next time I will have much funnier, kind of the crucial example, whatever. The most crucial example, I think, in this whole business. So we have the category of sets, and tensor product is just Cartesian product. It's not strict, we already had that. The strictification is what people call the skeleton. I will explain that next time as well. So skeleton. And the confusing thing is that if you look at here, so S is my notation for skeleton, essentially everything we see here is either already strict, like our diagram categories are already strict, that's good, or the strictification is a skeleton. So many people get confused and think the whole process of every category is equivalent to a strict category is just you go to this skeleton. That's not the case, and I will show you next time how that works. But for now, there is a way to do that, and essentially nothing you ever really see is not strict, except our friends are the diagram categories, right? The diagram categories, really beautiful. They're strict from the get-go. Nothing you can do wrong. You just stacked. Now, just as a reminder, why is that strict? Well, because here's our multiplication. You just stack diagrams next to one another. And, well, whether you do that 3 times, there are no brackets, right? There are no associators, there's nothing. You just stack diagrams, everything. Very beautiful and nice. And here in vector spaces or in sets, it's always a bit nasty. But you can somewhat forget it, right? That's kind of the whole point. And the way to prove that is, well, endofunctors of a category is strict, and essentially you can show that every category is equivalent to an endofunctor category. So in that sense, it's a strict category. But next time, as I said, there will be a really beautiful example illustrating this much more clearly. Anyway, I hope you enjoyed this video, and I also hope to see you next time.